talking about a case study on digital R&D. Jonathan.
Yeah, I might be a little bit different to the rest of the crowd today because I'm going to talk about our journey for digitising R&D. So this is clearly a precursor to manufacturing, but I think Alan's already touched on virtual prototyping. It's exactly the direction that we want to go. So first, who are we? So I think if you follow the news recently, every headline that's been about Unilever has either called us the Marmite maker or the maker of Ben & Jerry's, which is true, but there's a lot more to it than that. So we make some of the world's favourite brands. Here's the 12 billion euro turnover brands that are in our stable. You'll recognise some of them as household names, and you'll also recognise that not all of them are in the UK anymore because it's a global company with something like over 60% of the turnover now in developing and emerging markets, so a truly global company. So the turnover roughly is about 53 billion euros, and these brands touch about 2 billion consumers every day, so it's a big company with global reach. It's a company with a proud heritage, so it's a Northwest company in origin. Lord Lever, who founded the company around 1887, set up his factory at Port Sunlight, which is on the banks of the River Mersey. It's less than an hour's drive from here, and created a new model for selling commodities to the world in the sense that he invented packaged consumer goods. So that was the new business model of the day in 1887, and it's prospered to this day. At the time, the other groundbreaking approach that Lever took was to have a clear mission for his company, and at the time he was talking about making cleanliness commonplace, and we've updated that mission today. I won't talk too much about this, it's not the core of the presentation, but the mission today of the company is to make sustainable living commonplace. And that includes looking to double the size of the business while halve our environmental impact and improve the health and well-being of 1 billion people on the planet. So we've got a very clear stance on doing that. What we make, well, interesting portfolio. So it's large and diverse number of formats. You can there all the way from laundry unit dose tablets to mass market soaps, tea, cold supply chain with ice cream and margarine, liquids in pastes. So really quite a diverse set of formats. There are a few devices in the portfolio now. We've got some water filters that we sell in India and have rolled out to other parts of the world. I think the thing that characterises us, though, is we, by and large, are creating hundreds of millions of units a year. So the aerosol factory at Leeds creates 1 billion units every year. So this is a large-scale mass manufacturing. So the concept of mass customization of 1 billion units starts to boggle my mind a little bit. But I think, we shouldn't neglect the thought that could be the destination. But right now, I think there's the sort of billions and billions of units we make every year is probably not going to be where we're going to start with mass manufacturing. Sorry, mass customization. But that gives you the sorts of diversity of product formats and a sense of the scale of the operation that we're driving. So we do this in about 300 factories around the world with about 300 co-packers and third parties who help us with that. So it's a major manufacturing operation in that sense and extremely diverse. So if you think of the science base that feeds that, then actually we've built a really strong ecosystem in the northwest of England. So our own major, we've got 6 R&D labs around the world. The biggest one of them is at Port Sunlight. It's right next to the factory where it all started, which is great for the heritage of the place. There are about 800 scientists there. And what we've done over the past sort of 6 or 7 years is embarked on a deliberate strategy with partnership with the 3 partners you see there, the University of Manchester, the University of Liverpool and the Hartree Centre, which is very close to here and has got the UK's biggest supercomputer. And in each of those partnerships, we created programs that are essentially digital in nature. So with the University of Manchester, we're looking at complex fluid dynamics, process science, and all of that is digital. With the Hartree Centre, then all of our simulation is done there. Certainly all the simulation that needs high-performance computing, so very clearly digital. And with the University of Liverpool, we've built the Materials Innovation Factory, which is the middle diagram in this picture, which is an investment in robotics and high-throughput evaluation capabilities for R&D, which is a shared facility This was a major investment. It'll open this year for business, but I think we think it contains the highest concentration of open access lab robotics in Europe. And then finally, we're just about to open an advanced manufacturing centre at the Port Sunlight site, which will basically be our digital it'll create the digital twin of our factories once we get it up and running. So again, the themes that Alan talked about are very, very, very live in the R&D world in Unilever. Just quickly on the value of speed, this is old data, so clearly what's digitisation going to bring us? Quality, productivity, and speed, right? And the speed metric is quite an important one for us. The push to get to market faster is ever present, and these numbers have changed in that the best-in-class guys now are delivering to market in less than 12 months for an average innovation project in FMCG. So over the time of the past 4 years, then speed to market has improved dramatically already. And the first mover advantage genuinely does give an increment in sales. That's external data, but I can vouch that Unilever sees the same thing. So now this is where the video should start. There we go. Part of our journey to digitise has been to automate formulation. Now, this is not done carte blanche across the whole of Unilever's formulation capability, but you'd imagine formulation can be a mixture of an art and a science. So you're mixing and blending multiple components into a liquid or a solid or a powder or a paste. You can do plenty of measurements, but often it's the art of the operator that creates a great formulation. It's almost like painting at times. So what we've been looking to do is standardize the way formulation has done. And this has culminated in this robot, which can produce roughly 24 batches of, it's quite a large scale. An 800-gram formulation is big enough to do something with. You can then go and do some testing, figure out what it does on hair or skin or teeth or whatever substrate you're dealing with. And that basically transforms the efficiency of a formulator in a lab. So a formulator in a lab today manually can do 1 to 3 800-gram batches, and that's pretty low throughput. And the worst part of it is that there's really poor reproducibility, not within one person who've learnt the art, but between formulators. So data that's produced by different operators tends not to be easily comparable. So in creating our we call it Jeff robot, it's a robot that will be housed in the University of Liverpool Materials Innovation Factory from this year. It's open access because the UK government paid part of the cost of it. It'll mean we can standardise, automate and digitise in formulation and increase throughput. So this is actually a really big part of the journey towards digitising R&D. If you then look at the wider formulation journey, then okay, if you go back and look at many people's labs, they'll look like the second picture up on the diagram. So that's not a lot different from the first picture up on the diagram. And so these are pictures of our labs. The first one is the lab at Port Sunlight from around the 1920s. Right? The second one up is a modern lab. But there's not a lot different in there. Obviously, you're collecting data in Excel spreadsheets. If you go to the next stage, which I've just described, automated, then you can see the productivity starts to increase. But where we really want to go is in silico. So if you can predict how to formulate in silico, then you can absolutely step change your throughput and your productivity in terms of the number of formulations a person per day can create and test. So it's a tough journey. So it's the fully in silico is our ambition. If you wanted to, sorry, this gets to be a bit the science bit if you're not scientists, but if you want to try and simulate what an individual atom or molecule is doing on a surface, then if you want to simulate it atom by atom or molecule by molecule, it's very tough. You can do it in short time scales, a millionth of a second, with one atom or one molecule landing on one surface. So that's hopeless. We'll never, even with the best high-performance computing capabilities in the world, ever get to complicated mixtures with 20 or 30 components, all of which are interacting. And that's still in the static case. We've yet to get to what happens when you pump and you mix and you make things flow. So we've invented a technique called mesoscale modeling, which helps us to get there. It averages properties out across molecules so that we can make an approximation to what's going on at the atomistic scale, which is good enough to be able to predict what happens when we start to mix things together. So the mesoscale modelling, sorry, I'll go to that chart first. The mesoscale modelling really is now a commonplace tool in our lab. So we work with the Hartree Centre to get the computing power to do this. The example I'm going to give you is what happens when you mix a surfactant, which is the thing that cleans in laundry liquids, with water. These things form structures in water. They're very clever in that sense. That's what surfactants have always done. And if you want to formulate laundry liquids, you need to know what's going on. So they'll form into rods or hexagons or cubic phases, very, very elegant structures in solution. But if you don't know what those structures are and how they form, you can't formulate. So the traditional formulator would spend 3 months mapping out what we call a phase diagram. So against composition of water and surfactant and temperature, you figure out what phases form, and then you can figure out how to formulate. I did a PhD on this. It took me at least 3 months to do one of these. We can do it in 30 minutes using a mesoscale model at the high-performance computer at Daresbury. And so that's now an app that we can put on our formulators' desktops in Unilever. So it's really quite clever. It's only one part of the picture, but already we've made commonplace in the company the ability to do mesoscale modelling on a desktop. So now you can do these models without ever being an expert at that hard science that I just described. So we are thinking end-to-end. So computer-aided formulation at the beginning. We've got optimizer engines when we've got enough data, so you can start to build algorithms to predict how to formulate. The virtual twins there, virtual engineering packaging and virtual engineering processing are under development. We've got a pour flow simulation, which means we don't have to hard prototype pouring of liquids out of bottles. You can imagine how tricky it is to figure out how to design a bottleneck such that it doesn't dribble down the side. I mean, just an annoying thing like that consumers hate, we can now fix in silico, so we don't have to do hard prototyping. We've done some work on factory line optimization, and then ultimately the panel series manufactured to demand. But I think it's fair to say, and given the challenges of doing it on a 2 billion unit per year supply chain, we're further back there than we are at the front end of this journey. The next big challenge, of course, is these liquids, these complicated liquids, which form sophisticated structures, then get pumped and sheared and mixed all over the place in our factories. And the end property that you might find in a fabric conditioner or a margarine or a ice cream, whatever product you stick on yourself or eat, or its final microstructure and its final sensory properties or taste properties depend critically on the machinery we make it in and the shear regime that we make it in. And that's now even more difficult to simulate and predict. So our next big frontier is to figure out how to put this together end-to-end in silico. So we're hoping to do more work with the University of Manchester and perhaps some other companies in a consortium to build the next stage of this journey. Okay, and then I mentioned our digital twin at Port Sunlight. So we realized that between the formulation world and the world of creating prototypes and the factories, we needed something. We needed a much, much better capability for scale up. And so we've built one, but it's digital. So it's going to collect a massive amount of data on all of our formulations as we put them through, and packaging, by the way, as we put them through the process of taking them to scale. This is the sort of data engine that sits within that. I just taped my notes here because I can't remember and see from there. But basically, we can, when this thing is up and running, there'll be a mixture of data from the sensors that are in the hardware that's in this place. So the hardware is the equivalent of the machinery that we've got in factories, both for mixing, for liquids, and for packaging. So some of the processes that Alan talked about in capping, labeling, scrambling, and mixing, and so on, they'll be in there. But also the metadata that comes alongside, so the observations that are made during the manufacturing process, and then the capture of data from trials where we test the products on people and so on, so that we've got a total holistic data system that then is amenable to proper analytics, and then ultimately to being able to predict what's going to happen when we get down to factories. So just eliminating plant trials where instead of testing out whether you can make something in a plant, which takes production time away, upsets the factory managers you wouldn't believe, could be costly if we get it wrong because there's a huge write-off of raw materials. because you can't do a small run in a big Unilever factory. Just eliminating that saves millions of dollars every year. So many other business benefits, and ultimately the data that we capture in this facility will become the digital twin of our future manufacturing capability. So that's it. Some of our challenges still, you wouldn't believe, I mean, you think it's simple, but the science of these complex liquids is difficult. It's harder than crashing aeroplanes, seriously. And length scales do matter, so we have to figure out, well, both length scales and shear regimes and mixing regimes, because the final sort of microstructure is so exquisitely dependent on those things. In reality, we would like to centre up all of our factories, all of those 300 manufacturing units with that massive installed capital base, and also our partners. But the rate of capital renewal is not sufficient that we'll ever get there fast. So I think we've got to figure out a smarter way than this. And that does lead us with the challenge of turning primary data from our factories still into actionable models. So that's it from me. Thank you very much.